So hello, and let me welcome you to the talk about generalized Kochen-Specker theorem in 3 dimensions. It's a joint work with Mirko. Variable of orthogonal vectors is assigned 1. And now the generalization is that we don't want just 1 to be assigned 1, but an odd number of vectors in any orthogonal basis to be assigned 1. One such assignment is trivial, that we assign 1 to everything, so we exclude it and we want a vector to be assigned 0. I will be using some graphs to capture the vectors, so let me comment on this. So you are probably familiar, well, this is the Specker bug, and you are probably familiar with the rightmost diagram. The vertices in all these diagrams correspond to points of the R3, and the edges denote the orthogonality relations. So in the rightmost image, if there is edge between two points, then they are orthogonal. It holds in the middle image as well, but here there are also added vectors so that every edge is contained in a triangle. And so the rightmost is indeed a subgraph of the middle. And on the left, there is a hypergraph representation that will be used in this talk. And again, the vertices correspond to points, but now the edges, and it's a hypergraph edge. So edge is the maximal straight line segment. So there are 7 edges: 1, 2, 3, 4, 5, 6, 7. So every edge contains precisely 3 vectors, and it has the meaning that those 3 vectors form an orthogonal basis. So these 3 points are pairwise orthogonal. So it is equivalent to this orthogonality diagram, but for every triangle, we capture it only by an edge. It is clearly more simple than this, so it's better to use such hypergraph representation because we always need to have an orthogonal basis, because in the original Kochen-Specker graphs, if we have 2 vertices connected by an edge, then it has some meaning. It means that they can't be assigned to 1 simultaneously. But if we want for every triple of orthogonal vectors an odd number of them to be assigned 1, then if we have just 2 of them connected by an edge, then they can be assigned arbitrarily, and the third orthogonal vector will be assigned according to them. So if we have only a pairwise orthogonal relation and we want to assign those, we want to inspect the generalized case, then it's not sufficient. So we need this hypergraph representation. And yeah, it's probably more clear than this one. So here, if we want to the assignment, then we just assign the 1s and 0s to all these vertices, so that in every edge, an odd number of them is assigned 1. So either 1 or all 3. So we proceed with construction, and we will build it gradually. So here there are 3 edges, and first we start with ABC. It's a clearly an orthogonal basis. Then we have here parameters x and y. We will specify them later. These are some non-zero parameters. Yeah, and then we have E. Then the D is clearly orthogonal to C, and E is a cross product of C and D. So it's the cross product is a vector that is orthogonal to both of them. So they form an orthogonal basis, and similarly here. And this construct will be used throughout the construction. That if we have 2 orthogonal vectors, then the cross product cross product of 2 vectors is orthogonal to both of them. So we proceed with adding H as orthogonal to G and E, and adding those I and J that will form the orthogonal basis. So H is clearly orthogonal to G, and I is orthogonal to both G and H, so it can be added like this. And we repeat this process several times. So next we add K, and that is orthogonal to I and B, and add those L and N. And similarly for these three and these three. And so up to now, we have constructed such graph. So now we proceed, and we added this edge. So we want that L to be orthogonal to S and T. So for this we need this to hold, that the scalar product of L and S is 0. That means they are orthogonal. And similarly, we want an edge here that contains that J, U, and T. And U is orthogonal to J and T by construction, but we need to satisfy this orthogonality relation that J is orthogonal to T. So this is another equation we need to satisfy. So to construct such hypergraph, we had those two parameters, those x and y. So we have a system of two polynomial equations in two variables, and it happens to have solutions. So we have this solution. There are more solutions, but we can take this one. So now we have that this hypergraph can be embeddable to R3. That means we can assign those points, the points from R3 to the vertices, such that every edge contain vectors forming an orthogonal basis. And this is the starting point for our construction. So we proceed with application, how to get something from this. That we know that there are 13 edges, and every vertex is contained in precisely 2 edges, with the exception of U, O, and R, and they are contained in just one edge. So if we go through all edges and sum the sum the value of them on them, then we have value of A plus B plus C, and then for another edge we have that A, F, and G, and we go through all these 13 edges. So we have to arrive at 13, and during the process every vertex is counted twice. So like here we have A and A, and it's because they are contained in precisely two edges, with the exception that R, O, and U are contained in just one. So we are working in Z2. Then if we have twice something in the sum, then it cancels out. And here is 13, which is indeed 1. So we arrive at it. The value of R plus value of O plus value of U equals to 1 in every possible coloring. So we denote them here on the sphere. So here is A, B, and C, and they are necessarily sum up to 1. And it is independent of the choice of coordinate system that we can rotate this triple of vectors, and they still be the sum of the values will still be 1 here. So we can, for instance, rotate it like this, and still the values so sum of values here is 1. So we combine these two evaluations. So we have that A, B, and C. So we have that the B is equal and the C is equal. So we sum them up and get that this sum. So we sum this, and we arrive at that the value of here equals to value of here. So we have two vectors for which we know that
this means red A is something else than green A.
Yes, this is red A and this is green A. Yeah, so maybe I will talk a bit more about it. So here is the red A, red B, red C, green green A, green B, and green C, and they are chosen such that the B is equal. So if we like put them into a common image, then B is equal and C is equal. So there is those A and B that are not equal. So, and we know that sum of these valuations plus sum of these valuation is equal to 0, because 1 and 1 is 0 in the Z2. So we arrive at this, and since those B's equal, then this term cancels out, and C is equal, this term cancels out, so it remains that MA, M red A plus M green A equals to 0. That means they are equal in the Z2. So we know that the valuation of these two is the same. So we have these two yellow vertices, and they are same in every coloring. So it doesn't make sense to distinguish them. So we just say that they have some coloring, so some color, like the 1 or 0. And now we want to show that the only possible coloring is constant. That we showed on an example here. It is a bit technical to show it like generally. So we show that this black point is indeed assigned the same value as the yellow point. So we proceed like this. We know that these two green are the same because they we show that they are the same. Then we know these two reds are the same because they make the same angle as those two green. And finally, the yellows are the same in every coloring. So we had the black here formerly, so we arrived at that black here it has the same color to the yellow point here, and it can be shown for arbitrary point that it has the same color as this. So we arrive at the result that the only possible coloring, like the only possible assignment of zeros and ones to the vectors of R3, so that an odd number of them is assigned 1, is the constant 1. So clearly we can assign 1 to every vector and it will hold, but it's the only possible assignment. So that's all from me. I thank you for your attention, and please ask questions.
Could you repeat, please? Could you show again that slide with A and B's that are green and
this
one? Mm-hmm.
Here is A, here is B,
okay,
and here is C.
Okay.
So here is A, here is B, and here is C. So the B's are the same, and the C's are the same. So if we combine those two images, we arrive at the third one.
But my question is very related to this, but formulated in a different way. If I understood, the conditions that you have for the triples to add 1, they should apply to 3 orthogonal vectors, isn't it?
Yeah, yes, yes. We started with the...
Okay, so my second question would be, if this is the situation for both red ABC and green ABC, and we demand 2 of them to be equal, Shouldn't the third be in the same direction? So
Yes, thank you for the question. Well, I will return to this. We started this that if we have an edge that it connects three orthogonal vectors. That here P is orthogonal to R is orthogonal to Q, and Q is orthogonal to P. And also there are R, O, and U, which are not orthogonal. They are in some general position. But we know that if we sum the values of the coloring of every three vectors connected by an edge, we arrive at the fact that also the sum of these three values is 1, because every vector, every vertex is contained in two edges beside these three. So if we sum the values up, then every vector beside those three will be twice there, so that it cancels out, because we are like counting in Z2, so 1 plus 1 is 0. So twice something is 0 always. So we arrive at the fact that the value of R plus the value of O plus the value of U is always 1. And they are not orthogonal, they are in a general position. So from that we proceed to this, that we have three vectors in a general position. And we may rotate them, and the reasoning will still hold. So we have these vectors, and for both of these triples is hold that the sum of their values is 1. And now we rotated them such that those two will be the same, those two will be the same, and the third one will be different. So we had these two equations, and we summed them up. So we have that the value of red A plus the value of green A plus the red B plus the green B, red C, green C, and it equals to 1 plus 1, which is 0. And now we have those two B's equal, so this is the same, thus it is 0. Similarly, this is 0, and we arrive at the red A, which is this, and green A, which is this, are equal in every coloring. And they are not orthogonal here. These three vectors are not orthogonal.
This is Mirko Navarra as a closer. May I try to summarize? Three vectors behave like orthogonal ones, but they are not. But they behave like that as constant state, the states, Z2 states. And therefore, the value of the green A and at the green A and red A is the same, but they are not the same vectors. And that's the principal trick, because now we can say any state attains the same value on these two elements which are in a more or less general situation, general position, and then we extend it to any couple of vectors. If you want to prove a Kochen-Specker theorem, you have it here in an alternative way. What we gain more, that this is applicable also to evaluations in Z2 instead of real ones, and this was not achieved for the three-dimensional case before. It was known for higher dimensions, but 3 dimensions remained a mystery for 25 years. Now we have an answer. Yes, it can be extended to that.